this calculus video, we're going to learn how to sketch a curve. I'll show you the items that you need to consider when analyzing a function, and then walk through 4 examples so you'll know exactly what to do when you're sketching a graph on your own. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by going over everything you need to consider when sketching a curve. The items that I've listed below are everything that you should consider, but keep in mind that not every item will be needed for every curve. You want to start by looking at the domain. In particular, you'll need to check where the denominator equals 0 if you have a denominator, or where a square root is negative, and those values will be excluded from the domain. You then want to look at intercepts. To find the y-intercept, you just let x be equal to 0 and then find f of x. And then for the x-intercept, you let f of x be equal to 0 and then solve for x. Next is symmetry. With symmetry, you want to find f of minus x. If it's equal to f of x, then you have symmetry about the y-axis. And if it's equal to minus f of x, you have symmetry about the origin. And if you don't have either of those, then your graph won't be symmetric. It's best to then look at asymptotes and end behavior. You'll have a vertical asymptote at a point where the denominator equals 0. You'll have a horizontal asymptote if the degree of the numerator is less than or equal to the degree of the denominator. And then you'll have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. And then to find the end behavior, you need to find f of x at plus or minus infinity. The last 3 items can be found by looking at the derivatives of the function that you're graphing. To find where a function is increasing or decreasing, you will need to find the critical values, and then look to the left and right of these values. Your function will be increasing when f prime is greater than 0 and decreasing when f prime is less than 0. To find the local maximum and minimum values, you can use the first derivative test or the second derivative test. With the first derivative test, you're going to see where f prime changes sign. And with the second derivative test, you're going to find f double prime at the critical values. The last item to consider is concavity and inflection points. To see where a function is concave up or concave down, you'll need to find where f double prime is equal to 0, and then look to the left and right of those values. Once you have the concavity, you can find the inflection points, and an inflection point will be where the concavity changes. Let's now walk through our 4 examples so you can see exactly how all of this works. Let's sketch the graph of the polynomial f of x is equal to x cubed plus 6x squared plus 9x. We'll start by looking at the domain. Because our function is a polynomial, its domain is going to be all the points from minus infinity to infinity. Now let's think about intercepts. I think it's always easiest to find the y-intercept first. So to find the y-intercept, all we're going to do is we are going to set x equal to 0. And looking back up here at our function, that gives us that f of 0 is equal to 0. So our intercept is 0, 0, which is the origin. And that is our x and y-intercept. Let's now look at the symmetry. To find the symmetry, what we're going to do is we're going to calculate f of minus x. So wherever we have an x in our function, we're going to plug in minus x. This gives us a minus x cubed plus 6 times minus x squared plus 9 times minus x. This is minus x cubed plus 6x squared minus 9x. If we compare this to our original function, it is not the same, and it's not the negative of that function. So that means that we don't have any symmetry. So let's just say this is not equal to f of x or minus f of x. And for our symmetry, we'll put none. Let's now look at asymptotes and end behavior. Because our function is a polynomial, we are not going to have any asymptotes. So let's put down a none for the asymptotes. And then for the end behavior, what we're going to do is we're going to find f at infinity and f at minus infinity. One thing that is really nice when we look at end behavior is when we have a polynomial, the end behavior is going to be solely dictated by what we call our leading term, which is x cubed in this function. So all we really have to do is look at x cubed. So we can say that f at infinity is approximately x cubed, which is infinity cubed. So we can say that our function, as x goes to infinity, is going to go to infinity. And then f at minus infinity is approximately x cubed, and this is minus infinity cubed, and we'll say this is minus infinity. So as x goes to minus infinity, our function is also going to go to minus infinity. Let's now look at the intervals where the function may be increasing or decreasing. I'm going to start by writing down our function because we're going to need that. F of x is equal to x cubed plus 6x squared plus 9x. To find where the function is increasing or decreasing, we need to find the first derivative. So f prime at x is 3x squared plus 12x plus 9, and we are going to set that equal to 0. We can factor out a 3, and we have x squared plus 4x plus 3. And we can factor this as x plus 3 and x plus 1. This gives us the solutions x is minus 3 and x is minus 1. We can now draw a number line. We'll label it x, and we're going to put these critical values on it, minus 3 and minus 1. And I'm going to put an f prime here just to remind ourselves that we are looking now at the value of f prime. So let's go ahead and let's highlight that. We can just look at the leading term, and that is 3x squared. So when x is in this region right here, our f prime is just going to be like x squared, and that is going to be positive. And then in our region to the right, it's also going to be positive. Now what we need to do is pick a point in between minus 3 and minus 1. I'm going to choose minus 2, so we're going to calculate f prime at minus 2. Looking up at the yellow function, this is 3 times minus 2 squared plus 12 times minus 2 plus 9. This is 3 times 4, which is 12, plus 9 is 21, minus 24. We don't care about the value. We just need to know if it's positive or negative. This is negative, so we're going to put a negative up here. And now let's add some increasing and decreasing lines. This is increasing, decreasing, and increasing. Let's write down that it is increasing on the region from minus infinity to minus 3 and from minus 1 to infinity. Then we'll say that it's decreasing on the interval from minus 3 to minus 1. Let's now look at where our function may have a local max or min value. Based on the number line that we just drew, you can see that we are going to have a max at x is equal to minus 3, and then a min at x is equal to minus 1. So let's say we're going to have a max at x is equal to minus 3, and then we have to find what this maximum value is equal to. So I am going to go ahead and rewrite our function because we're going to need this. It is x cubed plus 6x squared plus 9x. Now we're going to find f at minus 3. Minus 3 cubed is minus 27. And then we have 6 times minus 3 squared, which is 9, plus 9 times minus 3, which is minus 27. And this is equal to 0. So we can say that we have a local max equal to minus 3, 0. Now let's do the same thing for our local min. We are going to have a min at x is equal to negative 1. So we're going to calculate f at minus 1. This is going to be easier. This is minus 1 plus 6 minus 9, and this is equal to minus 4. So we have a local min equal to minus 1, minus 4. Now we just have one more item to calculate before we can throw all of this together on a graph. Let's look at the concavity and inflection points. When we find concavity, we need to find our second derivative. To find f double prime, I'm first going to put f and f prime up here. We're going to need f for the inflection point. F is x cubed plus 6x squared plus 9x, and we found that f prime was equal to 3x squared plus 12x plus 9. Now we can find f double prime. That is equal to 6x plus 12, and we're going to set that equal to 0, and that's going to give us that x is equal to minus 2. Just like we did for increasing, decreasing, let's go ahead and let's draw a number line. And we're going to put minus 2 on our number line, and then we're going to look at the value of f double prime. Let me highlight that. That is what we are looking at. If we have a point that is less than negative 2, we can say like negative 3, f double prime is negative. And then if we have a value greater than negative 2, like 0, it's going to be positive. So our function is going to be concave down in this region and concave up in this region. So let's write that it is concave down in the region from minus infinity to minus 2, and then concave up in the region from minus 2 to infinity. Now we need to think about inflection points. An inflection point is where the concavity changes, and the concavity changes when x is equal to negative 2. So that is going to be our inflection point. Let's now find the y value of our inflection point. So we're going to calculate f at minus 2. Looking up here at our function that I highlighted in pink, we can find f at minus 2. So this is minus 2 cubed plus 6 times minus 2 squared plus 9 times minus 2. This is minus 8 plus 24 minus 18, and that gives us a value of minus 2. So we can say that our inflection point is the point minus 2, minus 2. Now we can go ahead and put all of this on our graph. Let's go back up to the top. I think the best thing to do is to first put all the points that we calculated on it. We found that we have an intercept at 0, 0. Let's go down here and see what else we found. We have a local max at -3, 0, and a local min at -1, -4. So our max is -3, 0. That's right here. We'll just put a little max here. And then our min is at -1, -4. That is right here. We'll label this min. And then our inflection point was -2, -2. So let's just put a little IP here for inflection point. Now let's go back and see what else we found. In part D, right here, we found that our function is going to be going to infinity when x goes to infinity and minus infinity when x goes to minus infinity. One thing we can do is just put a little line here and a line here to know which way our graph is going. Then we found that it is increasing as we get to -3 and then decreasing, and then at -1 it starts increasing again. So it's going to be increasing and then decreasing and then increasing. So we can actually go ahead and let's graph our function. It's going to come this way. We're going to go up to our max, and then it's going to be concave down till this point, and then the concavity changes, and it's going to be concave up, and it's going to pass through this point and continue going that way. Now let's go ahead and let's erase our other lines. And there we have our graph. We're now going to sketch the graph of a rational function. F of x is x squared divided by x squared plus 3. Just to make things easier, I already calculated the first derivative and the second derivative, so we can just focus on learning how to graph the function. Let's first look at the domain. We have to check if the denominator is equal to 0 because we have a rational function. X squared plus 3 cannot ever be equal to 0 because of the x squared term. So for the domain, it's going to be all values of x. So let's write down -infinity to infinity. Let's now look at intercepts. We're going to start by finding the y-intercept because that's easier. To find the y-intercept, we are going to let x be equal to 0. So looking up at our function that I highlighted in yellow, if we plug in x is 0, we get that f is also equal to 0. So this tells us that our intercept is 0, 0, and that is both our x and y intercept. Now let's think about symmetry. To find the symmetry, we need to calculate f at -x. So wherever we have an x in our function, we're going to plug in -x. This gives us a -x squared, all divided by -x squared plus 3. And this is x squared over x squared plus 3, which is the same as f of x. This tells us that our graph is going to have symmetry about the y-axis. Now let's look at the end behavior. I am going to go ahead and rewrite our function because we can't see it anymore. It is x squared all divided by x squared plus 3. When we look at asymptotes, we want to see where the denominator is equal to 0. In our function, it isn't, so we have no vertical asymptote. But now let's think about horizontal asymptotes. When you calculate a horizontal or a slant asymptote, you need to look at the highest power in your numerator and the highest power in the denominator. Those two powers are the same, so that tells us that we have a horizontal asymptote. And to find what that horizontal asymptote is, we have to think about the limit as x goes to plus or minus infinity. We're going to do this really informally. F of x is going to look like x squared over x squared, because only the leading terms count as x gets really big. And this is equal to 1. So we can say that our horizontal asymptote is y is equal to 1. Let's now look at intervals of increasing or decreasing. To find increasing or decreasing, we need to take the first derivative and set it equal to 0, or see where it's undefined. Our first derivative from up above was 6x, all divided by x squared plus 3 quantity squared. It's never going to be undefined, but it is going to equal 0 when x is equal to 0. So if we set that equal to 0, we get that x is equal to 0. So we can go ahead and draw a number line, and we're going to put 0 on this, and we're going to look at f prime. We want to find if f prime is positive or negative. Notice that the denominator is positive, so we don't even have to think about that. We just have to look at the numerator. Let's pick a number less than 0, like -1, and we see that f prime is going to be negative, and then to the right, it's going to be positive. This tells us that our function is decreasing in this region and increasing in this region. We can say then that it is decreasing on the interval from -infinity to 0, and it's increasing on the interval from 0 to infinity. Let's now think about local max and mins. Looking up at part E, you can see that we are going to have a min when x is equal to 0. So let's go ahead and let's write that down. We are going to have a local min at x is equal to 0. And we saw when we were doing our intercepts that f at 0 was equal to 0. So we can say we have a local min at 0, 0. So that's just a min at the origin. And from our graph in part E, we can see that we have no local max. So let's write down no local max. Let's now look at concavity and inflection points. For the inflection point, we're going to need to find the value of f at a point. So let's go ahead and write down what f is again. F is x squared, all divided by x squared plus 3. To find concavity, we need to use the second derivative. So let's write down what that is. That was given up above, and it is 18 times 1 minus x squared, all divided by x squared plus 3 quantity cubed. We need to find where f double prime is equal to 0. So this is just where 1 minus x squared is equal to 0. And this gives us that x is plus or minus 1. Let's now go ahead and draw our number line. And now we're going to put 2 points on it, -1 and 1. And we are looking at the value of f double prime. Because our denominator is always positive, to find the value of f double prime, we really just have to look at this term right here and see if it's positive or negative. If we let x be in this region, say x is -2, then f double prime is going to be negative. In this region, we could say x is 0, so it's going to be positive. And then in our right region, if we say x is 2, it's going to be negative. This tells us that our function is then concave down, concave up, and concave down in those regions. Let's go ahead and let's write that down. it is concave down. In the region from minus infinity to minus 1, and in the region from 1 to infinity, and then it's concave up in the region in between, which is minus 1 to 1. We are going to have an inflection point at -1 and at 1. I'm going to come up here and look at our function f, and we need to find what it's equal to at -1 and 1. Because we have an x squared, it's going to be the same value for -1 and 1. So f at plus or minus 1 is going to be 1 over 4, so 1/4. So we're going to have two inflection points. The first one is -1, 1/4, and the second one is 1, 1/4. Now let's go ahead and put all this information on our graph. I think the best place to start is by putting all the points that we calculated and put those on our graph. We found that we have an intercept here at the origin. We have a local min there, and then we have inflection points at -1, 1/4, and 1, 1/4. So -1, 1/4 is right here, and 1, 1/4 is right here. Now let's see what else we can add to our graph. We have a horizontal asymptote at y is equal to 1. So let's go ahead and let's put that in. And let's keep in mind that our graph is symmetric about the y-axis. Now let's look at increasing, decreasing, and concavity. It is increasing on the right side of the graph and decreasing on the left. And then it is concave up in between the two inflection points. So we're going to have concave up and then concave down. And that's it. It really helps to calculate all of this information first, and then it's pretty easy to graph the function. Let's now learn how to sketch the graph of the rational function f of x is equal to x squared divided by 1 minus 2x. Students always find this example challenging because it has a slant asymptote in it, but I'll walk you through exactly how to graph it. Just to make things easier, I went ahead and calculated f prime and f double prime, so we can just focus on the graphing and not have to worry about the derivatives. We're going to start by looking at the domain. Whenever you look at the domain of a function, you always need to be concerned where the denominator is equal to 0. So let's take the denominator of our function, 1 minus 2x, and we're going to set it equal to 0, and that gives us that x is equal to 1/2. This actually means that we are going to have a vertical asymptote at x is equal to 1/2 because our function is not defined at that point. Our domain then is going to be all points from minus infinity to 1/2 union 1/2 to infinity. So we're just going to bypass x is equal to 1/2 because that's where we have our vertical asymptote. Let's now look at intercepts. I think it's easiest if we start with the y-intercept. So to find the y-intercept, all you do is you let x be equal to 0. And if you look up at our function right up here, you can see that when x is 0, f is also 0. So we can say f of 0 is equal to 0. So our intercept is 0, 0. And this is both the x and y-intercept. Now let's think about symmetry. To find if our function is symmetric, we need to calculate f at minus x and see what that gives us. Wherever we have an x, we're going to put in minus x. So we have a minus x squared, all divided by 1 minus 2 times minus x. This is x squared, all divided by 1 plus 2x. When we compare this function to our function up above, we can see that they are not the same and they're not negatives of each other. So we can say that this is not equal to f of x or minus f of x. So that means our function does not have any symmetry. So let's just write down none. Now let's think about asymptotes and end behavior. We already found that we have one asymptote. We have a vertical asymptote. X is equal to 1/2. Now we have to think about other asymptotes. Let me go ahead and rewrite our function so we can have it in front of us. It is x squared, all divided by 1 minus 2x. Whenever you think about a horizontal asymptote or a slant asymptote, you need to look at the leading term in the numerator and the denominator. Notice that the numerator is 1 degree higher than the denominator. That tells us that we are going to have a slant asymptote. To find what our slant asymptote is, we have to do long division. I have a video on this if you need to review that. Hang with me, it won't be that bad. We are going to have x squared and we're going to divide it by 1 minus 2x. So up here under this bracket, we're going to put x squared, and then I'm going to change the order and I'm going to say minus 2x plus 1 as the part that we're dividing. It just makes it easier. Now we have to think x squared divided by minus 2x is equal to minus 1/2 x. So that's what we put up here, minus 1/2 x. And then we go ahead and multiply both terms. Minus 1/2 x times minus 2x is equal to x squared. And then 1 times minus 1/2 x is minus 1/2 x. Then we subtract, so we get a 1/2 x left. And then we have 1/2 x divided by minus 2x. That is minus 1/4. So we put that up top. And there's our answer. That wasn't too bad. So we can write down that our slant asymptote is y is equal to minus 1/2 x minus 1/4. Now we also have to think about end behavior. To find the end behavior, let me write this down. We only need to look at the leading term in the top and the bottom. So we can say f is approximately x squared over minus 2x, and this is minus 1/2 x. As x goes to minus infinity, we're going to have minus 1/2 times minus infinity, so that's infinity. And then as x goes to infinity, f is going to go to minus infinity. So our graph is going to be going up as we go to the left, and as we go to the right, our graph is going to be going down. Let's now look at increasing or decreasing intervals. For this, we need our first derivative, so let's write down f prime of x is equal to 2x minus 2x squared, and then our denominator is 1 minus 2x quantity squared. We are going to set this equal to 0. So we have 2x minus 2x squared is equal to 0. We can factor out a 2x, and that gives us 1 minus x is equal to 0. So this tells us that x is equal to 0 and x is equal to 1. We can then go ahead and draw a number line and put these points on it. We have 0 and 1, and we are going to be looking at f prime. We just need to know if f prime is positive or negative. Notice that the denominator of f prime is positive, so we don't really have to worry about that. We just have to look at the numerator. The other thing that we need to add to our number line is where our function f prime is undefined. We found that the denominator is going to be equal to 0 at 1/2. So let's put a little dotted line here, because what happens is sometimes our function can change from increasing to decreasing at a vertical asymptote. So we have to put that in our graph. Now let's pick a point to the left of 0 and see what our yellow function is equal to. So that is 2 times -1 minus 2 times -1 squared. So this is -2 minus 2. That is negative. So we'll put a negative right here. Now we have to pick a point between 0 and 1/2. So let's pick 1/4. So 2 times 1/4 minus 2 times 1/4 squared. That is going to be positive. So we'll put a positive here. And now let's pick a point to the right of 1/2. So let's pick maybe 3/4. That is also greater than 0. So we're going to put a plus here. And then if we look in this region to the right of 1, the only thing we have to really look at is this term right here. That's the biggest term. It is negative. So we know that f prime is going to be negative. That was pretty complicated, but we did it. Let's go ahead and put increasing and decreasing lines. Our function is decreasing here, increasing on each side of our vertical asymptote, and then decreasing here. Let's go ahead and write that down. It is increasing from 0 to 1/2 and from 1/2 to 1. Notice we cannot say that it's increasing at 1/2 because we have a vertical asymptote there. And then it is decreasing from -infinity to 0 and from 1 to infinity. Let's now look at local max and mins. If we go back up to our graph, we can see that we are going to have a local min at 0 and a local max at 1. Let's write that down. We have a local min at x is equal to 0, and we have a local max at x is equal to 1. Now what we have to do is find the value of the function at both of those points. So let me put that our function f is x squared all divided by 1 minus 2x. So f at 0, let's see, that is 0 over 1, so that's just 0. And then f at 1 is 1 over 1 minus 2, so that is minus 1. We can then say that our local min is 0, 0, and our local max is equal to 1 minus 1. We have one more thing to calculate, and that is concavity and inflection points. To find concavity, we always need to look at the second derivative, so I'm going to write that down. F double prime of x was 2 all divided by 1 minus 2x cubed. We can see that f double prime is never going to be equal to 0. But let's go ahead and let's look at our function again. Our original function is x squared divided by 1 minus 2x. Concavity can change where our function is undefined, and that is going to be at 1/2. Let's go ahead and let's draw a number line, and let's put the point 1/2, and then we'll have a little dotted line here because we have a vertical asymptote there. Now what we're going to do is we're going to look at f double prime to the left and right of this point. Here, we could pick a point x is equal to 0. And let's look at the value of f double prime. It is going to be positive. And then to the right here, we could let x be equal to 1. And f double prime is going to be negative. So this tells us that our graph is concave up to the left of our vertical asymptote and concave down to the right. We have concave up from minus infinity to 1/2, and then we have concave down from 1/2 to infinity. Because we do not have a point where the concavity changes, it only changes at an asymptote, we have no inflection point. Let's write down no IP. Now let's go ahead and put everything that we just calculated on our graph. I think the best thing to do is to put our asymptotes and our points on our graph first. We found that we have a vertical asymptote at 1/2. So I'm going to go ahead and put this on our graph. And let's go down here and see what else we have. We have a slant asymptote, and I'm going to put our slant asymptote up here. We found that our slant asymptote was y is equal to minus 1/2 x minus 1/4. Let's go ahead and let's graph this. Let's see, when x is 0, y is minus 1/4. So we have this point right here. And then when x is minus 1, we have y is equal to 1/2 minus 1/4, which is 1/4. And that point is right here. Now we can go ahead and draw our asymptote. Try to be as neat as we can. Now let's see what else we can put on here. Going down, we have a local min at 0, 0 and a local max at 1 minus 1. So here is our min, and then our max is going to be right here. And let's see, increasing, decreasing. It's increasing on either side of our asymptote, and then decreasing on the right and left of our max and mins. And it is going over here, concave up to the left of our asymptote. Now I think we can go ahead and draw our function. It's going to hug the asymptote, and it's going to come down here, and it's going to curve up. And then it's going to be concave down, so it's going to follow this asymptote, reach our max, and then follow this asymptote. And that's it. We are going to sketch the graph of our function f of x is equal to x divided by x squared minus 9. This is a classic function to graph. It is a rational function, and we are going to have both horizontal and vertical asymptotes. Just to make things easier, I have written down our first derivative and our second derivative, so we can just focus on graphing and not have to worry about those calculations. We are going to start by looking at the domain. Whenever we think about the domain, we want to look at points where our function might be undefined, and that is going to be where our denominator, x squared minus 9, is equal to 0. And this is going to be at x is equal to plus or minus 3. So we can say that our domain is going to be from minus infinity to minus 3, union minus 3 to 3. We're just bypassing minus 3 and 3, union 3 to infinity. And then let's also go ahead and write down that we are going to have a vertical asymptote at the points that are not in our domain. And that is where x is equal to 3 and x is equal to minus 3. Now let's look at intercepts. I think it's easiest to find the y-intercept first. So we're going to let x be equal to 0. And if you go back up here to our function, you can see that f of 0 is equal to 0. So our intercept is 0, 0. And this is both the x and the y-intercept. Now let's go ahead and look at symmetry. I'm going to go ahead and rewrite our function because that's what we're going to have to look at. It is x divided by x squared minus 9. To find symmetry, what you want to do is you want to find f at minus x. So wherever you have an x in the function, we're just going to plug in minus x. So this is minus x, all divided by minus x quantity squared minus 9. And this is minus x, all divided by x squared minus 9. And you can see that this is minus f of x. This tells us that we are going to have symmetry about the origin. So let's write down it is symmetric about the origin. Let's now look at asymptotes and end behavior. We already found that we have a vertical asymptote. Now we need to think if we have a horizontal asymptote. Let's look at our f again. It is x all divided by x squared minus 9. When we think about a horizontal asymptote, we are only concerned with the leading term in the numerator and the denominator. So we can say that f is approximately x over x squared, which is 1 over x. And this tells us that the limit as x goes to plus or minus infinity of f of x is approximately 1 over plus or minus infinity, which is 0. So this tells us that our horizontal asymptote is y is equal to 0. The other thing that we need to do is look at end behavior, and we can look at this function again to do that. As x goes to infinity, that's going to go to 0, and same thing as x goes to minus infinity. So we can write down that f at plus or minus infinity is equal to 0, and that is directly connected to our horizontal asymptote. As x goes to plus or minus infinity, we're going to go to 0, and we're going to go to that horizontal asymptote. So these match up for a reason. Let's now look at increasing and decreasing intervals. For increasing and decreasing, we need to look at the first derivative. I'm going to write down f prime of x. From up above is minus x squared minus 9, all divided by x squared minus 9 quantity squared. And we need to set this equal to 0. This gives us x squared is equal to minus 9. That can never happen. So our derivative, f prime of x, is never going to be equal to 0. So no critical values from that. But we may get critical values where f prime is undefined. It's undefined at plus or minus 3, but our function is also undefined there. So we have no critical values. A function can change from increasing to decreasing at a critical value or at a vertical asymptote. So I'm going to go ahead and draw a number line. We're going to label this x, and we're going to put our two asymptotes on it. We had one at minus 3. I'm going to put a dotted line there, and then a dotted line here for 3. And we're going to need to find the value of f prime to the left and right of those values. Notice that the denominator that I highlighted here in pink is positive, so we don't have to worry about that. We just need to look at this part right here. minus x squared minus 9. If we pick a point to the left of minus 3 in this region, f prime is going to be negative. If we pick a point between minus 3 and 3, f prime is also going to be negative. Just plug in maybe x is equal to 0. And then if we pick a point to the right, it is also going to be negative. So our function is decreasing in all three of these regions. Let's write that down. It is decreasing on minus infinity to minus 3, union minus 3 to 3, union 3 to infinity. And let's just write down that it is never increasing. Let's now think about local max and mins. Because our function is decreasing and it doesn't ever switch from decreasing to increasing or vice versa, we have no local max or mins. The last thing that we need to look at is concavity and inflection points, and we need the second derivative to do this. So I'm going to write down our second derivative, f double prime is 2x times x squared plus 27, all divided by x squared minus 9 cubed. Whenever I tested students on this, I always gave them the derivatives because I wanted to make sure that I was testing on the graphing and not on calculating derivatives, because that second derivative is pretty complicated. We are going to see where this is equal to 0. It is equal to 0 when the numerator is equal to 0. X squared plus 27 is never 0, so we're just going to get that x is equal to 0. And let's go ahead and let's draw our number line. We're going to put our value x is equal to 0. And then don't forget, we always have to put our vertical asymptote values on here too. This is minus 3 and 3. Because concavity can change at a vertical asymptote, we are looking at the value of f double prime. Since our derivative is so complicated, in the left region and the right region, we only need to look at the leading term. So we're going to look at this leading term divided by that leading term. So we're going to say that f double prime is approximately x cubed all divided by x to the 6th. That's x squared raised to the 3rd. So this is 1 all over x cubed. So we're going to look at this in this region and in this region. In the region on the left, 1 over x cubed is negative, so f double prime is negative, and in the region on the right, it is positive. Now, we can't do that for these two regions in between, so I'm going to let x be 1 and then negative 1. F double prime at 1, let's see, this is positive up on top. We don't care about the value, we just need to know positive or negative. And then negative down below, so this is less than 0. So we're going to put a negative here. And then f double prime at negative 1. The top part's negative, and then the bottom part is negative, and this is going to be greater than 0, so we can put a plus right there. Now we can think about the concavity. It is concave down here, and it's concave up here and here. We'll write down concave up from minus 3 to 0 and from 3 to infinity, and then concave down in the other two regions from minus infinity to minus 3, union 0 to 3. Now let's go ahead and put all of this information on our graph. I think it's easiest to start with our asymptotes. We found that we have a vertical asymptote at minus 3, So let's go ahead and let's put that in. And we have one at 3. Put that one in. And then we found that we had a horizontal asymptote at 0. I'm going to do this slightly above here so we can see it. Now let's go ahead and let's put in our points. We have an intercept at 0, 0. And do we have any other points? We do not. Now let's look at increasing and decreasing. It is always decreasing. So let's just draw a light pink line like this. It's decreasing, decreasing, decreasing. We'll erase that when we get done. And now let's look at concavity. It is concave up between -3 and 0 and 3 to infinity. So we're looking at concave up here, and then concave down here and here. Now we can go ahead and graph our function. To the left of -3, it's going to lie below the x-axis because it's concave down and we have to follow the asymptotes. So it's going to look like this. And then in between -3 and 3, it's going to change from concave up to concave down. So it's got to look like this. And then to the right of 3, it's concave up and decreasing. So it has to look like this. Now let's go ahead and let's erase all of these other pink lines. And there's the graph of our function. And that's it. You've seen how to sketch a curve step by step and work through 4 examples so you know exactly how to approach any problem. To get comfortable with the process, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.